Hello, this video is a virtual poster to tell you all about the research of the Dwatson group at the University of Delaware. So the major research interest within our group is actually the use of transition metal catalysis to form new carbon-carbon and carbon heteroatom bonds. So one of the largest areas within our group has been the work on heteroatomic Heck reactions and other cross-coupling reactions of heteroatomic electrophiles. We've also had a long interest in the C-Alkylation of Nitroalkanes, as well as the CH-Borylation and asymmetric reductive coupling. So the projects that are going to be discussed in this video include the Aza-Heck and synthesis of Indolines, multi-component coupling of Silyl-Electrophiles and Hiyama cross-coupling, Boryl-Heck and synthesis of diboryl alkenes, C-Alkylation of Nitroalkanes, directed CH-Borylation, and asymmetric reductive coupling. So the Dwatson group members who are going to be presenting the work in this video include myself. My name is Katerina Korch. I'm a 5th year graduate student in the group, and I have largely worked on Aza-Heck projects during my time here, and I will be telling you about Indoline synthesis. Alyssa will then tell you about silicon electrophiles. Ola will tell you about Boryl-Heck chemistry, and Raphael will tell you about nitroalkanes, as well as our 2 most recent papers on CH-Borylation and reductive coupling. So the very first Aza-Heck reaction was reported by Narasaka in 1999, and many other research groups have been interested in this type of transformation. And so what our group has really contributed to this field is to really identify new nitrogen electrophiles that are capable of participating in this reaction, which will give you a whole host of products that are not accessible using other Aza-Heck reactions. So unlike a traditional Heck reaction, where the electrophile is carbon-based, in the Aza-Heck reaction, the electrophile is a nitrogen. So in this case, we have within one molecule built in both our nitrogen electrophile and our alkene, typically to do a 5-exocyclization to give our cyclized product. So our initial work in 2016 was on lactams. This was followed up in 2018 with work on imidazolidinones. And most recently, we've been reported the use of this Aza-Heck technology to make indolines by using an aniline-based electrophile. So this is the work that I'm going to be telling you about today. So one of the first things that we had to tackle was to identify what actually our electrophile is going to be. And Fei Young, who was my coworker, who has recently graduated, was looking in the literature, and he was really inspired by this paper by Tompkinson, in which they do a simple partial reduction of a nitroarene to generate a species that does still bear a nitrogen-oxygen bond, which should be cleavable by oxidative addition with a palladium catalyst. And so we were pleased to see that this methodology was easily applied to more complex nitroarenes. So in this case, ones that also bear the alkene that will be required to do the Aza-Heck cyclization. So with our electrophile in hand, the next task was to identify the catalyst that we are going to use to do the Aza-Heck cyclization. And so we initially started with conditions from our prior work, which is to use this cod palladium dialkyl precatalyst, as well as a phosphite ligand. And though we were pleased to see that we did get some yield, 25%, we knew we had to do some screening in order to improve these conditions. So we looked at different ligands and also different palladium metal sources. We were actually happy to see that you could use palladium 2-DBA3, as well as a Arylphosphine ligand to give an 84% yield of the desired cyclized product. So with these conditions in hand, we wanted to see what our reaction was really capable of, what complex functional groups can we include, and what complex products can we make. And so we were pleased to see that most functionality was actually well tolerated. One exception is the aryl bromide was not well tolerated. And one thing that's actually particularly exciting about this work is that we're able to use more substituted alkenes. And so when you do the cyclization, you then generate a fully substituted center right next to the nitrogen. And since this is so sterically congested, this is often a challenge for a lot of indoline making methodologies. But we're really excited to see that our reaction was capable of making these really complicated molecules. So in a short summary, this work was published in Angewandte in 2019. There's 22 examples in the paper, and it does tolerate a wide variety of functional groups and complex ring scaffold. This paper was really well received by the chemistry community. It was ranked a VIP in Angewandte, as well as being featured in ACS's C and EN News. And it was also featured on campus in UD's UDaily newspaper. So next, I will pass it off to Alyssa.
Thank you, Kat. Hi, everybody. As she said, my name is Alyssa, and I am a third year in Don's group. And today I'm going to be, so Kat was telling you about nitrogen electrophiles, so I'm going to switch gears and tell you about our work with silicon electrophiles. So the three projects I'm going to briefly tell you about involve our work synthesizing vinylsilanes using a Silyl-Heck strategy, and then using a similar strategy to functionalize internal alkynes to generate tetrasubstituted vinylsilanes. And finally, I'm going to switch gears from electrophiles and tell you about our use of these tetrasubstituted vinylsilanes in a Hiyama coupling to generate tetrasubstituted alkenes. So to begin with the Silyl-Heck chemistry, my colleagues published the first Silyl-Heck paper in 2012 using both styrenyl substrates and aliphatic terminal alkenes. So the styrenes worked with excellent E-selectivity and yields. However, I pictured here are the aliphatic substrates, which unfortunately were limited to an overall 60% yield and showed several isomerization products of the alylsilane. So in order to improve this, my colleague Jesse in 2014 did excellent organometallic work and mechanistic studies in which he synthesized a library of Biaryl monoalkyl phosphines, such as the one pictured here. And he found that this ligand was able to improve the conditions and synthesize alylsilanes in excellent yields and selectivity. So from there, my colleagues wanted to eliminate the need for this thermally sensitive palladium catalyst. So in 2015, my colleagues were able to improve the first generation styrene conditions using palladium DBA instead, and this Jesse ligand, and maintain the E-selectivity while increasing the yields to up to 99%. So the most recent paper we published in this arena was in 2017, in which my colleague Sarah did a lot of mechanistic work and studying the solvent effects in this reaction. And she was able to synthesize and get a crystal structure of this palladium Jesse iodide dimer, which was really interesting. And she was excited to see that simply by using 1 mole% of this pre-catalyst, she was able to synthesize alylsilanes in excellent yield and selectivities. So I told you about these very, very briefly. And I encourage you to go read each of these papers because it's a really nice story that I can't get into right now. However, if you're interested, feel free to email me, and we are still working in this realm, particularly eliminating the need for silyl iodides and switching gears to silyl chlorides, which are much more stable, easier to work with, and commercially available. However, the challenge there is silyl chloride bonds are a lot harder to activate using palladium catalysis. So switching gears, I want to tell you about our most recent work, which we published in JACS this year, which used a Silyl-Heck strategy to synthesize tetrasubstituted vinylsilanes. So inspired by Murray's conditions in 1995, in which he used a silyl electrophile and a zinc nucleophile to functionalize terminal alkynes to generate trisubstituted vinylsilanes, my colleagues pursued this to similar conditions to get tetrasubstituted vinylsilanes. So starting with Murray's, briefly I'm going to tell you about the reaction optimization. And so my colleagues started with Murray's conditions in which the silane electrophile was added last. And unfortunately, they saw only trace product. However, simply by switching the order of addition to add the zinc nucleophile last, they saw a slight increase in yield. And then from there, they were adding the zinc over about a half hour, but slowing it down to an hour significantly improved the yield, which was exciting to see. And then by adding base and switching the palladium catalyst, they saw a jump to 70% yield, which was great. However, they wanted to improve it further. So they took a hard look at their mechanistic proposal as well as byproducts that are forming in the reaction. And they found this byproduct, pictured here up here on the right, in which you've got dimethyl ethyl phenylsilane, which we have a previous paper, detailing Silyl-Heck work, in which the zinc nucleophile can react directly with the Silyl electrophile, which you could imagine could be generating this byproduct. So my colleagues took a look at the possible mechanistic pathways that could be occurring, and they hypothesized that the palladium zero catalyst undergoes oxidative addition with the Silyl electrophile to get your to get this complex here, and then you've got two competing pathways, either with migratory and typical Heck migratory insertion with the alkyne, followed by transmetallation with the zinc nucleophile and reductive elimination to get your product, or you could have the minor pathway in which transmetallation is occurring directly with the zinc nucleophile to generate, and followed by reductive elimination to generate your Silyl-Heck product. So looking at the kinetics of this mechanism, my colleagues essentially hypothesized that in order to preferentially do the Silyl-Heck chemistry, they simply needed to increase the rate of this migratory insertion and decrease the rate of this transmetallation. And they figured that by doing that, in order to do that, they just need to slow the rate of addition of the zinc reagent to allow more time for the alkyne to react with the oxidative addition complex. And so gratifyingly, returning to the optimization table, if they increased the slow addition to 4 hours, they saw a jump to almost 90% yield, which was awesome. And then simply by changing the equivalence of each of the reagents, they were able to jump to a 95% yield. And then finally, something interesting to note is that when previously they were using diethyl zinc as the nucleophile, they were able to switch to ethyl zinc iodide and maintain the 95% yield. And the reason that this is important is because dialkyl zinc nucleophiles are pretty pyrophoric and have limited commercial availability, so that limits what we could put here at this position. However, alkyl zinc iodides can be synthesized with a variety of different reagents, so we could easily diversify this position. So from there, I'm not going to show you the complete scope of what they saw. Please check out the paper if you're interested. But as a brief summary, with aryl substituted alkynes, under these conditions, they synthesized 16 examples of tetrasubstituted vinylsilanes, diversifying each position, each R group, and they were able to get up to 95% yield and excellent syn anti-selectivity. So then they wanted to pursue alkyl substituted alkynes, and they started with 4-octine as the model substrate. And they thought that simply by changing the ligand, they could achieve this tetrasubstituted vinylsilane. So using palladium DBA chloroform as the palladium source, they explored a variety of different ligands to increase yield and selectivity. And you'll notice that by increasing steric bulk of the phosphine to this Druphos catalyst, they were able to get excellent syn and selectivity for the syn product, which is pictured here. However, as they increased the electron density of the complex and ultimately ended up at this at Jesse-Phos again, they noticed a huge switch in selectivity for the anti-product, which is pictured up here. Now, we hypothesize this is because the bulkier Druphos destabilizes the palladium vinylsilane intermediate and encourages a really fast reductive elimination. However, a smaller and more electron-rich Jesse-Phos ligand is able to stabilize this intermediate, which allows time for the weak alkene to isomerize to the anti-addition before reductive elimination. So from there, and as a brief summary, they were able to synthesize 12 examples up to 92% yield with excellent selectivity depending on the ligand of choice. So from there, knowing this, they went back to examine the aryl alkynes to try and get anti-selectivity there, and were gratified to see that by using the Jesse-Phos phosphine, they were able to synthesize the aryl substituted anti-vinylsilanes in excellent selectivity and yields. So for further information on this project, please read the paper or email me for any questions. It's excellent chemistry, and I encourage you to read further more than I can tell you. There's a lot more than I can tell you right now. So finally, having these vinylsilanes in hand, my colleagues wanted to explore a Hiyama coupling with them because there are only 4 examples in the literature of tetrasubstituted vinylsilanes undergoing Hiyama coupling, and then no examples of using an all-carbon silicon center, because most of the time silicon needs to be activated either by a fluoride source or have one of the substituents on the silicon be an oxygen in order to undergo Hiyama-Denmark coupling. So inspired by Anderson's conditions in 2004, in which he took a tetrasubstituted all-carbon vinylsilane and coupled it with an aryl iodide under palladium catalyzed conditions, my colleagues were able to optimize the conditions slightly to accommodate a tetrasubstituted vinylsilane to get the resulting product in 62% yield. I can't go into detail about this optimization, but please look at the 2020 paper I just talked about where they detail that optimization. Now, these tetrasubstituted alkenes are important core structures in medicinally and industrially relevant targets, such as tamoxifen, which is pictured down here, which is an anti-breast cancer drug. So we wanted to see if we could optimize these conditions further beyond the 62% yield. And my colleague Sarah wanted to start by eliminating the need for this toxic and expensive 18 crown 6 reagent. So she did a variety of different NMR studies to determine the mechanism of this reaction. And her proposed mechanism focused on the protodesylation step is where you have the potassium silanolate base made more nucleophilic by the 18 crown 6 sequestering the potassium ion, which then can attack the silicon center and facilitate the protodesylation mechanism to get your intermediate that then can couple in the Hiyama coupling mechanism. So my colleague hypothesized that in order to eliminate 18 crown 6, we simply need to facilitate this protodesylation process. Now, she examined a variety of different optimization conditions that I'm not going to go into, but you'll just have to wait and see with the paper. But one of the more interesting things she looked at is the substitution on the silicon center. And by increasing the electron density in the silicon center, unfortunately, she did not see any improvement in yield, nor with alkyl substitution at the silicon. And she also tried naphthyl substitution in order to see if breaking aromaticity could facilitate the protodesylation step. However, that didn't work as well. Finally, she found a furyl substitute. She synthesized a furyl substituted vinylsilane, and we were pleased to see that this actually did give yield of the expected tetrasubstituted alkene, which we hypothesize is because the furan can stabilize the carbocation in the protodesylation intermediate. So for further details on that, keep an eye out for the paper. And I'm not going to go into further optimization, but my colleague did work examining the ligand and the additive in this reaction, and we ended up optimizing the conditions to get the expected product in 98% yield. So as a brief highlight of the scope that we're going to have, this is only a few substrates of a larger table. So the aryl chlorides we can tolerate include alkyl chlorides, protected alcohols, esters, as well as heterocycles. And then on the vinylsilane side, we have alkylamines, again, protected alcohols, as well as other alkenes, and aryl substitution on the vinylsilane with varying electronics. So keep an eye out for that paper. I didn't go into much detail because we're hopefully going to be publishing it soon. And if you have any questions, feel free to email me. And from there, I'm going to pass it off to Ola to tell you about Boryl electrophile, Boryl-Heck chemistry with boron electrophiles.
Thank you, Alisa, and thank you, Kat, for the introduction. In addition to silicon electrophiles, we have also done work with the cross-coupling of boron electrophiles. The first of this series was the work published in 2016 by Dr. Reed, which showed the synthesis of vinyl boronic esters from terminal alkenes. And after that, it was followed by a second publication showing the synthesis of trisubstituted alkynyl boronic esters from alkenes using the Boryl-Heck reaction. And more recently, we have been working on the synthesis of 1,1-diborylalkenes through the same Boryl-Heck strategy. And I'm going to give you a summary of how we got from the first conditions to the current conditions we have at the moment. To kick off, I'm going to talk about the mechanism of this Boryl-Heck reaction. We believe this goes through similar classic mechanism like the Heck reaction, which is started off with oxidative addition, followed by migratory insertion into the alkene, and then subsequent beta hydride elimination generates the allyl or the vinyl boron species, and then reduction of the palladium 2 species to palladium 0 restarts the catalytic cycle. A closer look at the migratory insertion step shows that when multi-substituted alkenes are used as starting materials, there is increased steric repulsion during the migratory insertion step, showing that multi-substituted alkenes are porous substrate for Heck-like reactions. And if these alkenes were compatible with similar Boryl-Heck reactions, we should be able to achieve multi-substituted vinyl boronic ester products using this same strategy. And Dr. Reed was able to show that this is possible in his 2018 paper through the optimization of the previous conditions. He kicked this off by varying the boron electrophile that was used in this reaction. By going from CAD-BCl to CAD-BBr, a much more electrophilic source of boron was used, and with this, the product was observed in 63% yield. And by switching to a monoligated palladium precatalyst instead of a bisligated palladium precatalyst, the yield also went up to 95% yield. And he further showed that you can isolate this product 94% after 4 hours using 2 equivalents of CAD-BBr. With optimal conditions in hand, he was able to study the scope of this reaction, and he found that a variety of functional groups were well tolerated, such as aryl methoxy group, aryl amine groups, protected phenols, as well as heterocycles are well tolerated in this reaction, although pyridines don't seem to be compatible substrates for these conditions. And apart from 1,2-disubstituted internal alkenes, he also showed that 1,1-disubstituted alkenes are good substrates for these conditions. And he also showed this with various examples ranging from methyl substitutions to methylene substitutions on the carbon, showing the good scope of these conditions. And since then, we've since moved on, and currently we've been working or just finished the synthesis of 1,1-diborylalkenes using similar strategy. 1,1-diborylalkenes are useful compounds. They've been shown to undergo various reactions such as stereoselective Suzuki-Miura cross-coupling, oxidation to the corresponding carboxylic acid, and formation of the vinyl dihalide with the copper halide salt. There are various strategies in the literature, and if you want to look at them, you can see this review that I cited here. But this synthesis of these reagents from alkynes and alkenes is currently limited, as the current conditions that are known in literature that involves alkenes would usually give 1,2 addition when alkyl substituted alkenes are used as starting materials. Although it is noteworthy to mention that A recent paper by the Curie group showed that you can actually make 1,1-diber-related products with the use of alkyl-substituted or aryl-substituted alkynes. So we wanted to solve this problem in the literature where you get 1,2 addition with alkyl-substituted alkenes using the Boryl-Heck strategy, because we know that this is a very selective strategy and it would give the 1,1 addition rather than the 1,2 addition. Therefore, we started this by varying the amount of CAD-BBr required in the reaction. And by going from 2 equivalents to 4 equivalents of CAD-BBr, we noticed quantitative conversion of starting material to the diber-related product. And with optimal conditions achieved, we also went ahead to study the scope of this reaction, and it is safe to say that this reaction is compatible with a variety of functional groups ranging from electron-rich styrene to electron-poor styrene, as well as aryl halides, diophenes, and protected vinyl indole pattern. And apart from conjugated alkenes, we also studied the scope of unconjugated alkenes. And what we found is that these were also good substrates for this reaction, as these products were isolated in very good to good yields and showing good compatibility with alkyl chlorides, alkyl silanes, alkyl bromides, and ethers, as well as protected alcohols. In conclusion, we've been able to achieve the synthesis of vinyl bromates, disubstituted vinyl boronic esters, and 1,1-diberalkene through the use of Boryl-Heck strategy. And we are also looking forward to making even much more interesting products using this same strategy. At this point, I would give it to Ralph.
Hi, my name is Raphael, and I'm a fourth-year graduate student in Professor Don Watson's group. In addition to heteroatomic Heck reactions that Katerina, Alyssa, and Ola have described, our group has also worked on the nitroalkane chemistry along with the phosphonate-directed ortho-CH borylation and asymmetric reductive homocoupling of aryl halides. First, I'll be discussing about our work specifically on the C-Alkylation of nitroalkanes. So nitroalkanes are quite versatile intermediates in organic synthesis. They can be converted to a variety of functional groups, including amines and carbonyls, which are commonly found in biologically relevant molecules, and also participate in several carbon-carbon bond-forming reactions, such as the conjugation reaction, the nitroaldol reaction, and even palladium-catalyzed reactions such as the Bogwald arylation. Given the importance of nitroalkanes as valuable synthons, a potentially simpler approach to accessing highly substituted nitroalkanes would be through the C-alkylation using alkyl halides. However, this transformation actually turns out to be much more challenging than expected. The reason for this is because the nitrogenate anion that is generated in situ prefers to react with the alkyl halide through an O-alkylation, which forms a nitronic ester intermediate that rapidly decomposes under basic condition to generate aldehyde and oxime as products. Although efforts have been made in the past to overturn the chemoselectivity to favor C-alkylation, these methods proved to be limited in various ways. Now, our group became interested in developing a practical and mild approach to addressing this challenge. So we turned our attention to transition metal catalysis. And in 2012, our group reported the first C-alkylation of nitroalkanes with benzobromides using a copper bromide and 1,3-diketamine catalyst system. In the following years, we discovered that alpha-bromocarbonyls and alpha-bromonitriles could be tolerated as electrophiles under the same copper catalyst system. Lastly, and most recently, we discovered that propyl-bromides could also be used as electrophiles by switching the ligand to an ethylene diamine ligand. Preliminary mechanistic studies suggested that these reactions were proceeding through a single electron mechanism, and a major limitation in using these copper catalyst system was that an adjacent radical stabilizing group on the electrophile was necessary for the chemistry to work. So in 2017, we were able to address this limitation by switching to a nickel dibromide beta-Cooper catalyst system. And under these conditions, unactivated primary, secondary, and tertiary alkyl iodides were not tolerated. In addition, we recently discovered a chiral-nickel catalyst system that can induce asymmetry in the C-Alkylation reaction using alpha-bromo amides as electrophiles. Next, I'll be discussing about our collaborative work with Professor Tim Clark's group at the University of San Diego on aerophosphonate-directed ortho-CH borylation. Ortho-Boryl aerophosphonates are an important class of compounds that can be used to access highly substituted aerophosphonates. In addition, these compounds are also frequently used as precursors for the synthesis of phosphorus-based ligands. And a great example of this was shown by the Westcott group in 2014, where they were able to generate a bi-aero monophosphonate compound through a Suzuki-Miyaura cross-coupling reaction and further manipulate the phosphonate group to access a monophosphine ligand. A method that can be used to access ortho-Boryl aerophosphonates is through the Miyaura borylation reaction. However, this is limited by the starting material availability and adds more steps to the synthesis. A potentially simpler approach to the desired compound is through a directed ortho-CH borylation reaction. In the presence of transition metal catalysts, a variety of directing groups have been used to direct CH borylation, which includes carbonyls with basic nitrogen groups, phenols, silanes, dienes, ethers, halides, and phosphines. We envision that phosphonates could also be used as a directing group to access the desired borylated product. So we found called iridium ACAC and an electron-deficient phosphine ligand, as shown in entry 9, to be optimal for selectively borylating the aryl group ortho to the phosphonate. The substrate scope proved to be broad, tolerating varying electronic properties on the aryl group, along with varying substitution patterns. And heterocycles could also be used, as shown in the last two examples. To further showcase the utility of these products, we were able to convert the B-pen group to other functional groups, such as hydroxyls, chloro, bromo, and cyano groups. And this collaborative work was published in JACS last year and was also highlighted in SimFacts. The last project I'll be discussing about is on our most recent publication on the nickel-catalyzed asymmetric reductive homocoupling of aryl halides. Now, axially chiral biaryl bisphosphines are widely used as chiral ligands in asymmetric catalysis. And as shown in the box are several examples of these chiral ligands. A commonly used approach to access enantiomerically pure biaryl bisphosphine ligand is through an ohmic coupling reaction of the corresponding aryl halide to generate a racemic biaryl bisphosphonate or bisphosphine oxide. The enantiomers are then separated through resolution to obtain an enantiomerically pure biarine compound where the phosphorus center is further manipulated to access the desired chiral bisphosphine ligand. Now, a major drawback in this multi-step synthesis is the resolution step. This is because a tedious optimization of resolution condition is required, and more importantly, this provides at most 50% yield of desired H-O isomer. A direct asymmetric route to prepare enantiomerically pure biaryl bisphosphonates or bisphosphine oxides would ease the preparation of a chiral bisphosphine ligand. And we envision that the use of a chiral nickel catalyst could address this challenge. Through optimization of reaction condition, we found pyridine oxazine ligand 1 as the optimal ligand, and that cobalt phthalocyanine or cobalt PC, and the choice of reductant had a dramatic effect on the enantioselectivity of this reaction. As shown in the last entry, nickel dibromide DME could be used in place of air-sensitive nickel cod, and that the addition of Horningstar molecule sieves was observed to reduce the proto-dehalogenation byproduct. With the optimal conditions in hand, the substrate scope was evaluated and it proved to be broad. Both phosphonates and phosphine oxides could be tolerated with varying electronic properties, and substitution on the phosphonate group could also be changed. To showcase the synthetic utility, several biaryl bisphosphine ligands were synthesized from a single precursor. First, bisphosphonate 2 was converted to the bis-dichlorophosphate and then treated with various Grignard reagents to generate the bisphosphine oxides. Then these were reduced to the desired bisphosphine ligand in good yields and high levels of stereochemical retention. So excitingly, the conditions developed here also proved to be effective for other classes of asymmetric aryl halide dimerization. Ortho-bromo aryl esters, amides, and ethers could also be dimerized in good yields and high levels of enantioselectivity. This work was published in JACS this year, and this provides a novel approach to synthesizing chiral bisphosphine ligands. And currently, a collaborative mechanistic and computational studies are ongoing with Professor Oswaldo Gutierrez at the University of Maryland.